In this video, we're going to continue to talk about Chapter 2, and specifically we're going to talk about describing quantitative data. Okay? So, as I mentioned in the last video, when I have categorical data, there are only so many options that I have when I want to describe it. Okay, so when I take measurements of, well, not actually measurements, but when I observe people's eye color, okay, and then I want to describe that, summarize that in some way, the only thing I can really do is count up the number of people who have each category of the categorical variable. I can only count up how many people have blue eyes, brown eyes, green eyes, so on and so forth. But when I have quantitative data, I can do much, much more. Okay? And so, as I mentioned before, we're going to talk about 3 different measurements, sort of, when we look at a quantitative variable. So we can summarize it or describe it in 3 possible ways: shape, center, and sometimes called scale, sometimes called variability. Okay, so we'll start off with shape. Okay, or this is sort of tangent to shape. Okay, and it is modality. Okay, and that is how many modes does the data have. Okay, so as a refresher, the mode is the most common outcome in the variable. Okay, so that's a mode. When we talk about a quantitative variable, we can also talk about sort of how many humps, for lack of a better word, there are in the data. Okay, not the actual mode as like a single number, but that the data has like one peak in it. So you can have one peak, and if you have one, then then it's called unimodal. Okay? If there's 2 distinct peaks, then it's called bimodal, and then more than 2, it's called polymodal. Okay, and then now we get to shape. Okay, how the data looks as a whole. So, what we kind of want in this course later on, we'll find that being symmetric helps us, but some variables may be symmetric. Okay, and so symmetric is each side of the data around the center is a mirror image of each other. If you cut the graph or cut the plot in half and then fold one side over onto the other, they'll look the same. That's symmetric. Okay, symmetric data. And if it's not symmetric, on the other hand, it's skewed. Okay, skewed. One side of the distribution stretches out farther than the other side. There's a few different ways that you can be skewed. You can be left skewed and right skewed. Okay, or skewed left and skewed right. Now, let's focus on that bit for a second. Okay, so skewness, or the way the data is skewed, goes in the direction of the tail of the graph. So here are 2 histograms. Okay, you'll see on the left and the right. These 2 histograms are both skewed. Okay, and when I mean skewed, okay, just as we described or defined in the last slide, you'll see that the tail of the distribution, okay, and when I mean tail, I mean this right there, where it slowly dies off, okay, in the direction. That is the direction of the skew. Okay, so you'll see the graph on the left is skewed right. Okay, graph on the left is skewed right, and graph on the right is skewed left. Okay, maybe I should have changed those around so the left went with the place where the picture was. So when the tail goes off in that direction, okay, that's the way the skew goes. Some students get confused and say, well, most of the data, it looks like, is on the left of the skewed right picture. Okay, and so I should call that skewed left. The skewness refers to where the data points are that sort of don't match the rest of the data points, okay? And so this has to do with things called outliers that we will talk about in just a minute, okay? So just remember that skewness goes in the direction of the tail of the distribution. And the tail of the distribution are things that are far away from the center. So here's your turn to practice that skill, okay? There's a plot. I want you to tell me if it's symmetric or skewed, and if it's skewed, tell me the direction of the skew, okay? So hopefully that your turn won't be too challenging. Now, we can talk about the shape as we did in the last couple of slides, but we can also talk about the center and the variability. So first I want to talk about measures of center, okay? And they are the three that you're used to when you talk about the middle of the distribution or finding it: the mean, the median, and the mode. Okay, we're not going to talk about the mode here. We'll focus our attention on the mean and the median. So the mean, described in sort of a technical way, okay, or described in how you actually calculate it, is the sum of all the observations together divided by the number of observations. Now in this course, we're going to work with a bunch of different symbols, okay? Many people say that statistics is its own language of mathematics, okay? Certainly different than mathematics, and we have our own language associated with what we're working with, okay? So the mean is the sum of observations divided by the number of observations. So the mean, we're going to call it x with a bar on top of it, and I would say that, or I would speak that as x bar, okay? And so x bar equals the sum of all of the observations, and so in the numerator of this fraction that I have here, it's a capital sigma, okay, which in mathematics and statistics represents the sum. It's a sum operator, and I'm summing over all of the values. I called each value x, okay? And then I divide by n, where n is the number of observations I have. Okay, so it's the sum of x divided by n, and that is x bar, the mean. Okay, the median is the middle value of the observations when the observations are ordered from smallest to largest. Okay, there's no good formula that I can show you here for the median. Okay, but sometimes we call the median x with a tilde on top, or x tilde. That's less common, though. So the properties of a mean, okay? So sometimes I need to use the mean to represent the center. Sometimes I need to use the median. To understand when, I need to understand the properties of the mean and the median. So properties of the mean is that it's the balancing point of the data. So if I put weight on the data of like how far away they are from the center, okay, and I put like a balancing point at the mean, it would balance. It wouldn't tip over in one direction or another. Right? Usually the mean is not actually equal to a point in the data set. Okay? So the mean household, the mean number of children in a household, at least at one time, was around 2.4. Certainly you can't have 2.4 children, okay, but that is the mean number of children in each household. For skewed data, the mean is pulled towards the skew. Okay? This is a not so good property of the mean that we need to keep in mind when we're talking about measures of center. If I have really skewed data, the mean is maybe not the greatest idea to be the one that's reported. Okay? So, along the same line, the mean is highly influenced by outliers. What is an outlier? It's an unusually small or large observation in the data. Okay, so a common example that I and every other statistics professor might use is that if we all stood in class and we said what is our income, or maybe our parents' income. Okay, so we all say a number, and then someone like, I guess it used to be Bill Gates, but now maybe Jeff Bezos, who's the CEO of Amazon, would walk in and he'd tell us his how much money he earns in a year. Okay, his number is going to be much larger than any of our numbers. Okay, and so his is an outlier. And so if I took the mean of all the numbers that I had in the classroom, it's going to be much larger than all of ours, okay, because it's going to be pulled toward that huge number, okay? And similarly, small numbers can do the same thing. Properties of the median, okay, it's the true middle of the data. Okay? It is the actual middle point of the data by construction, by the way we found it, okay? And the median, unlike the mean, is not influenced as much by outliers, okay? And when something is not influenced by outliers greatly, it's called a resistance measure. So I'll use that term a lot, resistance measure, okay? If a measure, so like the mean or the median, is not resistant, is resistant to outliers, meaning that it doesn't change a lot, okay, then it's called a resistance measure. Using my same example, all of us in the classroom, and then some extremely wealthy person comes in and tells us how much money they earn in a year, the mean is going to be very much so pulled towards that person, whereas the median won't be pulled towards at all, okay, because it's going to be the true middle point of the data, which is going to be in the middle of everyone, not that outlier. As a visual example, here's some skewed data that we saw is similar to is similar to the skewed left and skewed right example. Okay, and so you'll see that there are some extremely large values compared to the rest of the data in here, out near 10, okay, and 8, maybe 7.5 and 7, a few small numbers out, larger numbers out there, okay, a small number of them, but the red line is the mean, okay, and the blue line is the median. So you see they're not terribly different, but the red one is pulled toward the skew more than the blue. Okay? The blue's not perfect. And you would think, well, maybe if it's perfect, it would be right on the tallest bar. Okay? That's not necessarily true, okay? But it looks like it's more toward where most things are happening than the mean is. Okay, so that's measures of center. We have the mean and the median. Right? What you should take away from that is if I give you a plot where the data looks to be skewed, and I ask you what measure of center should I use to describe the center of the data. If the data is skewed, you should say the median. Okay? If it's symmetric, you should say the mean. Generally, the mean is better, has nicer properties, something that we won't get into in here, but it has nicer properties than the median. Now on to variability. Measures of variability that we may or may not be familiar with are the range. Okay, we probably know the range. It's the smallest, the largest value minus the smallest value. But two other ones are the standard deviation and the variance. Okay, standard deviation and variance. The range, largest minus smallest. Okay, it's not a very good measure of variability. Okay, not a very good measure. The two that we're going to focus on, and it's really just one at the moment, is standard deviation and variance. So the standard deviation is the standard difference between the data point and the mean of the data. So what does that mean? It's kind of hard to really think about what the standard deviation does. It's probably simpler to say standard deviation gives us some number, larger standard deviations mean larger spread in the data. Okay, smaller standard deviations mean smaller spread in the data. You calculate the standard deviation, which we'll call S, okay, using this formula. It's the square root of what's called the sum of squares minus n divided by n minus 1. Okay, I won't go into why it's this because that's above our pay grade, so to speak, in this course. Okay, but there is the formula that actually calculates standard deviation. You should take away that the symbol that we use for standard deviation is S. Right? And then we get to the variance. The variance is just the standard deviation squared. Okay? So it takes away the square root. You may wonder, but why do we need different names for two things that are basically the same? Standard deviation has units associated with it, and the units are at the same level as the data. Okay, so if my units in the data were meters, then standard deviation would also have like meters sort of units associated with it, whereas the variance is going to have those squared units associated with it. And so it has a different meaning in some sense. So here are some quick properties of standard deviation and variance. The greater the variability, the larger the standard deviation. Okay. The standard deviation has to be a positive number. Okay. And it technically can be non-negative. It can be 0, but only when all of the points in the data are the exact same number. Okay. Like the mean, the standard deviation, and then thus in turn the variance, are affected by outliers. So the standard deviation / variance, both are not resistance measures. Okay, they're affected by outliers. I use the mean in my calculation of the standard deviation. Thus, if the mean is not a resistance measure, then neither is the standard deviation. So, how do we interpret S? Okay, it's kind of hard. From that definition, it wasn't very clear. Okay, and there's sort of different answers. Not sort of. There are different answers based on what the data looks like. Okay, or rather, when the data looks a certain way, certain interpretations that we're going to talk about don't make sense. So, in the nicest case, when the data is bell-shaped, okay, when the data looks like the shape of a bell, then we can interpret S more directly. Now, bell-shaped is going to come up a lot in this course, and for good reason. Okay, I in parentheses say after bell-shaped, normal. Okay, we're going to talk about normal data a lot, and when I say normal here, it's not in the usual English language interpretation of normal. Okay, meaning other data is like not normal, meaning that it looks weird or something. That's not true. Okay, any data that looks like a bell curve in some way or another, we're usually going to call that normal. There are different circumstances that we'll talk about later, but usually, if it looks like this picture below, then it's normal. Okay? And if that happens, we can interpret S more directly using something called the empirical rule. Okay? So the empirical rule is something that is fairly powerful, right? And so if you look at this plot, okay, at the bottom, the center of the data, the highest point on there is at X bar. It's at the mean. Okay, so it's at the mean, that's the center of the data. If the data is bell-shaped, it's also symmetric. Okay, so we talked about symmetric before. And it turns out when the data is symmetric, the mean and the median are the same thing. So it doesn't really matter what we use there. And like I said before, it's probably better to use the mean for various reasons. When I add and subtract the standard deviation from the mean, okay, so then I get to this point and this point here, the empirical rule says 68% of the observations lie between those points. Okay. When I go out to plus and minus 2 standard deviations out here and out here, that says that 95% of the data lies between those 2 points. And you may say, well, that's great, but why does that matter to us? In statistics, we're looking for maybe things that aren't common or aren't typical. Maybe look at data. Maybe I look at data about diamonds, and I have this diamond, and I take it to a jeweler. He tells me all about it, okay, and then tells me the price of the diamond. But I don't believe the price. Maybe it seems very low to me. Okay, I can go to this data. I say, well, these are the prices, okay, for diamonds about this size and everything. You are, sorry, diamonds that are this size, have this quality, so on and so forth. And the price that you're quoting me is much lower than all the rest, okay, based on this. Right? That's not really probably going to happen in real life, but hopefully that made some sense. Okay, and plus or minus. So back to the picture, plus or minus 3 standard deviations. That means that almost all of the observations are within that. Okay, to put a specific number on it, I believe it's 99.7% of the observations are between those two. Plus and minus 3 standard deviations from the mean. Right? So we're going to come back, since this video is too long already, come back and finish up by talking about measures of position in the next video.